Hello, we will now talk about Chapter 6, Section 3, which deals with binomial and geometric random variables. And so, first of all, let's talk about what is a binomial random variable in a binomial situation. A binomial situation is when you have a problem where they're going to give you a proportion or a percent. It'll say something like 70% of people in a city own a car, let's say. Then it'll give you a fixed number of trials, an N. Let's say the number of trials is 10. And then it'll say, what's the probability? So if you randomly select 10 people, that you have 6 successes. In other words, 6 of them own a car. So it'll, in essence, give you these, when it gives you these 3 numbers, a proportion, a fixed number of trials, and then a number of successes, that is a binomial situation in essence. Or, it could be any sort of defining success. It could say, someone, when they shoot free throws, there's a 70% chance they'll make the free throws. Then they shoot 10 free throws. What's the probability they'll make exactly 6? Or, in a big truckload of potatoes, 70% of the potatoes are rotten. So if you randomly select 10 of them, what's the probability that exactly 6 are rotten? So you're looking for the probability of a certain number of successes in a certain number of trials in P. And so when you're given these 3 things, that is in essence a binomial situation. Now, looking at it in a more formal way, this is what are the 4 conditions of a binomial setting. And this is the way your book describes it. And it spells out the acronym BINS, B-I-N-S. And so the first one is it a binary situation? In other words, all the outcomes have to be a success-failure situation. In other words, it can't be 3 options. It can't be like political party where it's Democrat, Republican, and other. Okay, or it can't be some sort of survey where you're asked, do you agree with this? Or do you strongly agree? Do you disagree? No, that's 4 options. Okay, it has to be a success-failure situation. All right. Secondly, do we have independence? In other words, the trials cannot be influencing each other in any way. So, like when the kid's shooting free throws, if he makes a free throw, he can't get encouraged and have that likelihood of making a free throw go up. Or he can't get discouraged and have that probability go down. The trials have to be independent. They can't be influencing each other. All right. The N stands for a fixed number of trials. So it's going to say something like you randomly select 10 people, or he shoots 5 free throws. Okay. A fixed number of trials. That cannot change. And lastly, the probability has to remain the same, the whole problem. Which is very similar to independence in essence. But it can't be a situation like when you're dealing cards where the probability of a king on the first card is 4 out of 52, and the probability of the king in the second card is 3 out of 51. Your probability just changed significantly. And so anyway, so here's the formulas, and this looks a little complicated, but and I'll show you these on the formula sheet, and I'll demonstrate these. They aren't critical, but they're as far as this one goes, and we'll talk about them. And so there's the formula for the mean. This is a basic binomial probability calculation, and we'll talk about that. There's the formula for the mean and the formula for the standard deviation. So on the formula sheet, so if you go to the front page of your formula sheet, so here's the chapter 6 stuff. So this stuff, discrete random variable, that's the stuff we did in 6.1. And then here is a binomial situation. So there's that formula I just pointed to. All right, there's the formula for the mean, N times P, and there's the formula for the standard deviation. And then geometric, which is the end of section 6.3, which we're going to talk about in a little bit. There's your basic calculation formula. There's your formula for the mean, and there's your formula for the standard deviation. So remember that these are on your formula sheet. And then one condition that's going to be important at some point is that your population size has to be at least 10 times your sample size. In other words, whenever you're sampling from a population, just make sure that in the 10% condition is that your sample size can't be more than 10% of the population. So that is an important condition, because the thing about it is when we're doing sampling with proportions, if you're taking too many out of the population, your proportion is going to change significantly. But as long as your population is big enough, your proportion won't change significantly, and it can still meet this condition of the same for the P being the same throughout the whole trial. So let's look at let's do some problems. That's the best way to really understand this stuff. And so this one says this: Fritz plays basketball. Each time he takes a free throw, there's a 60% chance he'll make a free throw. Fritz takes 4 free throws. So 60% chance, that's my P. And it does not change in the problem. It says each time he takes a free throw, it's 60%. So that's good. That would meet that condition. And there's our N. So our sample size or our number of trials is 4. Is this a binomial setting? And so you'd say, well, first of all, is it binary? In other words, is it a success failure situation? And that's yes, it is a success failure. Either he makes the free throw or not. There's no in between. There's no third option. So that is a binary situation. All right. So do we have independence? And yes, the occurrence of one trial is not in any way influencing the probability of another trial. So that's good. Do we have a fixed number of trials? We have a fixed N at N is equal to 4. So that good. So there's check for independence, check for fixed N. And lastly, P does not change. P is equal to 0.6, does not change. And so that meets the requirements for a binomial setting. So we would say yes. So anyway, so what's the probability that Fritz will make exactly 3 out of 4 free throws? All right, so here's your basic binomial problem. So our P is equal to 0.6. What's the probability that he's going to make exactly 3 or 4? I'm going to go ahead and show you the little shortcut on your calculator because this is what you're going to do most of the time. So we're going to use a function called binomial PDF. PDF for probability density function, or I think of it as a point. It's of a specific point. And so we're going to enter in these numbers, and we're going to enter in alphabetically. N is equal to 4, our P is equal to 0.6, and our X is equal to 3. So it's in essence saying, if I take 4 free throws, and there's a 60% chance I'll make each one, what's the probability we'll make exactly 3? So let me show you where this is on your calculator. So you can do these problems pretty quickly if you know what you're doing. So we're going to go to the distribution menu. Binomial PDF is below normal CDF down the list. So we're going to go second distribution, and we are going to go past normal CDF and inverse norm, past all this other stuff. There it is, binomial PDF and CDF. That's what we're going to do right now, but PDF for right now. So we go PDF here. And so our number of trials, and so we'd say, okay, our number of trials is 4. Our probability of success is 0.6, and our number of successes is 3. And so we hit enter. Now, many calculators will immediately take you to this screen. So if it immediately takes you to this screen, you just enter those numbers in that order. So let's say if this pops up on your calculator, so delete, 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 delete. So if this pops up, you would say, okay, enter them in alphabetically, N, P, and X. N is 4, comma, and then P is 0.6, and then comma, comma 3, and like that, and just hit enter, and there's my answer. So that would be 0.3456. Now, it's important that you label these with the letters. If you don't label these with the letters, you're not going to get full credit for showing your work. So this would give you full credit for showing your work, putting the letters there like that. And so that's how you do it. Now, having said that, you do have to be aware of how to use this formula here. And so let me show you once again on your formula sheet. So a binomial probability, right where it says binomial probability, there it is. Okay. And so what this notation here is, it's not really that critical you understand it because you can use this. All right. And what I'm fixing to show you is it's never really occurred in the exam except in multiple choice problems. It's a frequent occurrence. Well, they'll give you your answer in this form. So you have to be able to understand that the formula is here. And so that is going to be what we call N choose X, or I put it K here. That's the same thing, but N choose K. But N choose X, where it's P to the power of X and 1 minus P to the N minus X. And so what that would be is this, if I were asked to do that. So the probability of 3 successes, so that is going to be 4 choose 3. You might have had that previously in your math career, times, and then 0.6 to the third power times 0.4 to the first power. So the theory behind this is this. The probability that he's going to make a free throw is 0.6. So the probability that that's going to happen 3 times is 0.6 to the third. Well, if he misses free throw 3, if he makes 3 free throws, that means he's going to miss 1. And so the probability of failure, 0.4, is happening 1 time. So that's the probability of 3 successes and 1 failure. And this number is the number of different ways they can occur. Okay. In other words, it could be he makes the first three and misses the fourth one, or it could be he makes the first two, misses the third one, and makes the fourth one, and so forth. That's the number of different ways that can happen. So this number, I don't want to get too distracted here, but this 4 choose 3 thing. So what that is, it is 4 factorial over 3 factorial, and then the difference factorial. That's what that is. And 4 factorial is 4 times 3 times 2 times 1 over 3 factorial is 3 times 2 times 1. And 1 factorial is just 1. And so the 3 times 2 times 1 is canceled. And so it's just 4. So this is going to be 4 times 0.6 to the third times 0.4 to the first. And so let's see what that is. So that is going to be 4 times, and then 0.6, and I'm going to raise that thing to the third power. That's the raise to the exponent button, raise to the third power, and then right arrow over, and then go times 0.4 to the first power. And so that's that. And so that is how you do that. And so having said that, yes, that's tedious to do. The only thing that's ever been in the exam with this formula is they give you the answer in this form. They give you this problem, and then the multiple choice answer looks like that. And so, of course, the other ones will be different formulas that aren't this, but you have to remember that formula is right there. So you look on your formula sheet, whichever one matches that formula in your formula sheet, so there you go. And last thing I'm going to show you, it's really, once again, I hate showing you all this stuff that's really not that important. This is the main thing you got to be able to do, okay, to be able to get the answer. Okay, well, anyway, but let me just go ahead and show you the shortcut for 4 choose 3. The shortcut for 4 choose 3, which I did there, is in the math menu. If you go to math and probability, and there it is, that's in choose R right there. So and you could do 4 and then enter 3 like that, and boom, it's 4. Yeah, so there you go. So that's how you do that. All right, so then it says this: show the binomial probability distribution of X, the number of free throws Fritz makes when he shoots 4. What is a probability distribution? It is every possible outcome with its probability. So what's every possible outcome for X? What's the number of makes that he makes when he shoots 4? So it could be 0, he could make 0, he could make 1, he could make 2, he could make 3, he could make 4. And so the probability distribution is finding the probability of each of those. So we just found it for 3, so that's 0.3456. So let's find it for the others. And so back in the old days, we'd have to use this formula 5 times, okay? But we have this handy calculator here. And so what we'll do, I'll just go arrow up and capture that command again. I'll just change that to 0, change the X to 0. And so boom, so that's 0.0256, 0.0256. And then what's the probability of it being 1? So I hit enter there, replace that with 1. And so that's 0.1536, 0.1536. And so then I'll arrow up again and replace that with a 2. And so that's 0.3456, which coincidentally is the same thing as 3. And then lastly, I will find what's the probability he's going to make all 4 free throws is 0.1296. 0.1296. And we could make a histogram like we did in the first section. You could be asked to do that, but I won't do it here because we did it in the first section. So there's the probability distribution of a binomial situation. All right, now find the mean and standard deviation. So the mean, it's a simple calculation. Remember on your formula sheet, there it is. For a binomial situation, the mean is just n times p. N times p. And so it's going to be n times p. And so in this case, that is 4 times 0.6. And that is 2.4. So in the long run, we're expecting him to average 2.4 makes whenever he shoots 4 free throws. So the standard deviation is right there. So binomial situation, the square root of n times p times 1 minus p. And so this would be the square root of 4 times 0.6 times 1 minus that, which would be 0.4. And so let's see what that is. And so that would be the square root of 4 times 0.6 times 0.4. So that is 0.9798, 0.9798. And so that is how you do the mean and standard deviation of a binomial situation. So, okay, great. So now this is important. Being able to state it's always important to be able to state the mean and standard deviation in context. So the mean is the average, is what the points average in the long run. If you looked at many trials, it's what the points average, okay? The standard deviation is, if you looked at many trials, it is the average amount your points are gonna vary from the middle, from the mean, okay? And so in this situation, this is the way we would word how we describe the mean and the standard deviation of a binomial situation. So for a binomial, our mean, our mu is 2.4. If we looked at many trials, in other words, if Fritz took 4 free throws many times, we expect him to make on average 2.4 of them, okay? And whatever you do, don't round that number. It's a long-term average. It's not what we're expecting him to make when he does it one time. We're expecting it's a long-term average if he did it many times. The standard deviation of that, what does that mean? Or interpret that. To interpret that, if Fritz took 4 free throws many times, all right, the number that he would make will vary from the mean of 2.4 by 0.9798 on average. Okay, so we wouldn't be surprised at all for him to make 3.4 or for him to make 1.4 somewhere. So anyway, so that's the mean and the standard deviation. So interpreting the mean and the standard deviation. So all right, so here we go. Now, Fritz shoots 8 free throws. What's the probability he'll make at most 6? All right, so at most 6. So he could make 6, 5, 4, 3, 2, or 1. So that situation we have is this. If he shoots 8, what is the numbers that he could make? Well, he could make 0, 1, 2, 3, 4, 5, 6, 7, or he could make 8. Okay, so we are looking at the probability he's going to make at most 6, which is 6 or below. One option would be to use our formula, which we just did. So one option would be to use that formula, which we did on the other side of this. We could use, back in the old days before we had binomial PDF and binomial CDF, we could do this formula a whole bunch of times. Well, back in those, the easy thing to do there would be to use the formula to find the probability for 7 and 8 and then subtract it from 1, because these probabilities have to add up to 1. But we have a function that tells us not just the probability of one value, but of all the values and below it. In other words, the accumulated probability. That's what we call binomial CDF. So binomial CDF. Now, CDF means cumulative. It's not the value of one value, but everything below it. And so we enter in, so binomial CDF, we're in our N, our sample size is 8. Our P is still 0.6. And now our X is less than or equal to 6, like that. And so let me show you where that is. And so we go to second distribution right above the vars button, and it's right below. Scroll down, second distribution. There it is. Binomial CDF means cumulative. So P means for 1 point, C means cumulative. So our number of trials is 8. Our probability of success is 0.6. And X, our number of successes, is 6. And so there we go. And some calculators will immediately take you to this screen, similar to the PDF. And so you just hit enter there. And so that would be 0.8936. Boom, like that. So that's the easy way to do that. Like I said, used to, we would find the probability of 7 and 8, add them up and subtract it from 1. And that would tell us that. All right. And then it says this: if Fritz shoots 8 free throws, what's the probability he'll make at most 4? So what's that situation? So, well, he could make 0, 1, 2, 3, 4, 5, 6, 7, or 8. Or what's the probability he make at least 4? Make at least 4, that's 4 or more. So now using CDF directly, we don't have a function that tells us the probability of 4 or more, but the CDF is cumulative. In other words, it tells us the probability of a certain value or below it. So what we could do is find the probability of 3 or less and subtract it from 1, because these probabilities have to add up to 1. They have to add up to 100%. And so the probability that X is going to be greater than or equal to 4 is just going to be 1 minus the probability of that not happening, which is X is less than or equal to 3. So the greater than functions, that's what you got to do. And so this is 1 minus, and so this would be binomial CDF of, and once again, our N is equal to 8, our P is equal to 0.6, and then our X is less than or equal to 3, like that. So let's do that. And so we will say, so we'll just use that, and we'll say 3 and below. So our X is 3, which since it's CDF, it's 3 below, 3 or below, 3, 2, 1, or 0. And so that's that. So this is going to be 1 minus 0.17367. And so if we say 1 minus the answer, and so that would be 0.8263. There we go. So that is how you do that, and that's binomial. Then our other situation that we have is a geometric situation. Now, geometric is very similar. It is also a binary situation. Also has to be binary, has to have a success failure. Just 2 options have to be defined in the problem. You can't have 3 or more options for your outcomes. All right, we'll also have to have independence. Okay. In other words, the trials cannot influence each other in any way. The outcome of one trial cannot influence the probability of another trial. Our P has to stay the same. P cannot change, But, and here's what's different. We don't have a fixed number of trials like we do in binomial, but we are concerned. We are concerned with when is the first success. That is all we care about in regards to first success, in regards to geometric. In binomial, we're saying, well, you know, if we have 5 trials with probably 3 successes, that sort of thing. But in a geometric situation, it'll say, when is your first success? So it could be something like you're trying to find someone to do a job for you. You don't need 3 people, you just need 1 person to do it. Or you're trying to find someone to go to homecoming with. It's not like, well, if I ask 10 people, what's probably 3 you're going to say yes. No, you just need, when is that first success? Or you're doing, you know, something in regards to the probability of a plane crash. Well, a plane crash, I mean, it's not going to happen more than once. I mean, once the plane crashes, it's done. So when is the first success, so to speak? So here's your formulas. And so on your formula sheet for geometric, so it's right there. So for your geometric distribution, there's our general geometric calculation. There is the formula for our geometric mean. There's the formula for our geometric standard deviation. So there we go. And so let's, and so there's those formulas. And so let's look at this situation. So Gustav is looking for someone to fill a job opening at his axe factory. Each time he interviews someone from the field of applicants, there is a 0.1 probability that he will interview an applicant that is qualified for the job. Okay, so he's not really concerned with, you know, 5 successes out of 7. He just needs 1 person. He needs 1 success. So it says, what's the probability? The first qualified applicant. So you're saying that's geometric. Geometric is, when is your first qualified one, will be the 7th one. All right, think about this. Our probability of success is 0.1. So that means our probability of failure is equal to 0.9, right? If there's a 10% chance of success, there's a 90% chance of failure. Sometimes in some books, you'll see this written as Q, but we don't. So anyway, so think about this though. If the first success is on the 7th one, what does that mean happened on all the first 6 trials? It means they all had to be failures. So it had to be the probability that's 0.9 to the 6. That's the probability of 6 failures. And then the 7th one is a success, and the probability that's 0.1. So that's that. And that's what that formula is. This is saying that the probability that your first success will be on the kth one is 1 minus p to the k minus 1. In other words, that's the probability of failure. That's the probability of 1 minus k, and then that's your first successes on the next trial. So, but hopefully intuitively this makes sense. If your first success is on the 7th one, it means you have 6 failures and 1 success. And so let's make that calculation. And so that's going to be 0.9 to the power of 6, and then times 0.1. And so that's 0.05314. So that would be 0.05314. So there we go. All right, so what is the probability that it will take 10 interviews for Gustav to encounter a qualified applicant for the first time? And so with this one, that it would take at least 10. So think about this, that if it takes at least 10, it could take 10, it could take 11, it could take 12, it could take 13, and so forth. We don't know when the first success was, but what do we know about these first 9 interviews? They were all failures. If the first success was 10 or after, the first, and the probability of failure is 0.9. The probability of that happening 9 times is 0.9 to the 9th, okay? And we don't know when our success was. We don't know if it was the 10th, 11th, or 12th, or whatever. That is our answer. The probability that your first success is on a certain value or after it is just that many failures. And so it's 0.9 to the 9th, okay? And so that's what that little formula means. And so, so this would be 0.9 to the power of 9. And so that would be 0.38742. You know, and the proof of that involves looking at the series, the probability that the 10th one's the first one, the probability the 11th one's the first one, and then the 12th and 13th and so forth on to infinity, and it converges to that number, but that's not important. Okay. And then we have, you know, what is the mean? All right. So the mean, once again, when you look at your formula for a geometric situation, the mean of a geometric situation is just 1 over p. So our mean is equal to 1 over 0.1. And so that's 10. So what that means is, on average, if we were to do this many times, he would see the first qualified person on average on the 10th trial, okay, if we looked at many trials. In other words, if we had Gustav enter a number of people until he gets his first success, a number of people until he gets his first success, again and again and again, okay, it would average on to the 10th one. And lastly, I do want to, the formula for the standard deviation is that, and they just put that on the formula sheet. It hadn't been on there in previous years, and it's never been in the exam, but they put it on there, so I guess maybe they're going to use it. So the standard deviation of this situation is the square root of 1 minus 0.1 over 0.1. And so that would just be the square root of 0.9 over 0.1, and let's see what that is. So this would be the square root of 0.9 divided by 0.1. And so that's 9.487. So 9.487. And so that's the standard deviation in that situation. And that's it. That's section 9.3 for you. Thanks for watching the video. If you have any questions, please send them to me. I'd love to hear from you. Have a great day.